Let me get started. Welcome everyone to Settle3 webinar. And today we have a new exciting feature that we would like to present in this webinar called CPT simulation. Just a brief introduction about rock science. We are a world leader in developing innovative 2D and 3D software for civil mining and geotechnical engineers. We have over 25 years experience, and we've built the geotechnical tools that is used over by 10,000 users around the world. And we're dedicated to delivering industry-leading software programs, exceptional customer service, and unparalleled technical expertise that engineers can always rely on. Just a brief introduction of some of the programs that we have for Settle and foundation analysis. We have FEM programs such as RS2, RS3, Settle3, and RSPile, RSData, DIPS, and RSLog. And these can all be used to accurately model and analyze foundations, embankments, surface loads with 3D settlements and pile analysis software. And we can do CPT, SPT, and liquefaction analysis. And we have option to do wick drains and so much more. So I encourage you to check it out in our website. And for anyone who is new to Settle3, it's a very robust and flexible and fast settlement analysis program at Rock Science. And this powerful tool allows you to analyze the immediate, primary, and secondary settlement with embankments, foundation, and surface loads. And also has CPT analysis, which we'll go over more in details in this webinar, liquefaction analysis in the program. So with many features, it's very easy to create the SOL profile, and you can also assign ground improvements and many other features, and Settle3 will be able to provide you with the flexibility that you need to run and accurately analyze the settlement. So without further ado, let me introduce myself. So my name is Steve. I'm a project manager at Rock Science. I deal mostly with Settle3 and our pilot program. I've graduated from University of Waterloo as an undergrad in my postgrad at University of Toronto. And now I'm working there full-time at Rock Science. And we have a guest presenter with us, Dr. Cheng. He's a distinguished professor at Department of Civil Engineering in National Taiwan University. Dr. Cheng is a distinguished professor in the Department of Civil Engineering at National Taiwan University. He's received a PhD program in 2002 at University of California at Berkeley. His main research is based on geotechnical risks and reliability, random fields, spatial variability, probabilistic site characterization, and geotechnical data analytics. So today's overview of the webinar, I'll go over the CPT simulation in Settle3. But first, let me start off with our existing tools, what we have had so far in allowing users to input the CPT and run the analysis and see the results. But we have a new feature which allows users to now simulate the CPTs. Given the CPTs, if you'd like to see how your CPT will look like in between the points, we'll try to cover some examples on how to do that with this new feature. And you can also run the empirical settlement using CPT simulations, which means that as long as you have the given CPT points, you will be able to generate a defined region where the users can analyze and see the SOL profile settlement, the empirical settlement. So I'll try to explain more in details on how to do that and what results that you expect to see. Now, this sounds very magical to say, but we have all these implemented behind the scenes with a very complex algorithm, which Dr. Cheng will assist us in explaining that with our technical background of random field simulations. So how we are actually using our data with spatial variability, conditional random fields, and Gaussian process regression to get those data and what the simulations actually mean behind the scenes. So the Settle3 has the CPT analysis, which is basically the interpretation of the CPT analysis, and that can also be used as a liquefaction input data. So we have the interpolation that can be used. The CPT data can be used to also create the SOL profile for non-horizontal soil layers with our feature called section creator. So I'll try to explain more in details. And as long as the user provides the CPT with the QC, FS, and U2 parameters, then they can do the CPT analysis in Settle3. So the analysis flow looks like this. So as long as you have the CPT data, then you simply import or enter the CPT points, and you compute the CPT analysis, and you'll be able to see the results. So the CPT analysis option in Settle3 is defined from the project settings. under the tab of CPT. As soon as you enable that option, then you have in the toolbar under the CPT tab, you have all these options coming available for you, and can simply run the CPT analysis and get the results. And on the right-hand side, you will see additional features called CPT simulation, the settlement region with the CPT, and statistical analysis in using the CPT simulation feature. So how CPT analysis is done in Settle3? We first go to edit the CPT data, and as long as the user enters these data points for QC, FS, and U2 for the corresponding CPTs, then those, you can place it anywhere in the plan view in 2D, and that will be shown in the 3D view as well. And once you run the analysis and you right-click on the CPTs and you go to Graph CPT, then you'll be given the input parameters as well as the results. That gives you all the parameters that are correlated off of the given CPTs. So as you can see here, you have the results such as stress normalized current resistance, to stress normalized friction ratio, and even to soil classification along the depth of the soil with the given CPTs. And you can also do what's called a total model chart mode that allows you to plot multiple CPTs on the same graph. So you get a general sense of how your CPT is distributed with respect to the other CPTs. And of course, all of these results can be exported to Excel as well. So in case if you are interested in looking at more in details for each of these correlations, then you can do so using the export to Excel feature. And what can we get out of the CPT inputs? So these are all of our CPT outputs. There are a lot of parameters that users can extract from the CPT analysis. So the common ones are the friction ratio, normalized QT, Young's modulus, relative density, fines content, and all of these soil classification that is obtained from Settle3 using the CPT analysis. And we have a soil classification method that allows users to see the soil behavior type values along the depth of the soil. So as you can see, when you go to CPT soil classification, for each of these corresponding CPTs, you should be able to see the soil classification along the depth. And we choose the highly likely percentage of the soil types for a given depth, ranging from the user-defined value. And that soil profile can be generated as a soil layer system in Settle3. But note that these are simply soil behavior types, and these are not actually representing the actual soil layers with soil properties. So what we would encourage the user to do is to go back to the CPT analysis results with the Young's modulus or any parameters that they want to see. And then they would have to do some sort of engineering judgment in between the defined delta size of their CPT values and the results, and then apply corresponding soil properties for the layers that we provide for the users with this soil classification. So that's one thing to take a note when using the CPT data for a soil layering system. And again, once you have these soil layers defined from this classification, you can simply go to what's called a section creator. So section creator allows you to define any soil profile that you want in the cross-section view. So you can think of these as sort of a boreholes that is generated with the CPT soil classification layering. And then you can simply draw any shape that you want, whether it be the grass surface at the top, and then inter layers in between these boreholes can be freely drawn. And what Settle3 will do is that it will generate a 3D orthogonally extruded full soil model from these CPTs. So this is just to go over the existing features that we had before regarding CPTs and up to what extent can you use these CPT points to run the analysis and create the models. Again, if you are interested in looking at this distribution of the SPT zones for given CPTs, you can do so by going to one of the options called SPT zones, and you can do the dropdown, and there'll be a lot of soil classification methods that you can select to see how your distribution looks like. And of course, we have a rapid CPT import as well. So in case if you have the database of all the CPTs that you'd like to import and then click of a button, you can do so using the data forensics. And we are also in current development of integrating potentially with R's log to have all the CPT points integrated into Settle3 as well. Now, these are the data support types that we provide for the users if they have CPTs and other data format that we can simply import all of these different data types into Settle3. So let's move on to the new feature, which is the CPT simulation and empirical settlement with the CPT points. So CPT simulation, it allows users to simulate CPT at any location given CPT points. As magical as it sounds, it actually is based off of spatial variability using what's called a non-lattice Sparse Bayesian Learning algorithm. And it is all based on the correlation between the given CPTs. And we use the number of simulations to estimate how likely the CPT points will be in between the points. And Dr. Chim will provide more details and some of the verification examples that they have done in their research to show the confidence level and how credible, how valid, like you can verify the results. And so I won't go into too much details on the mathematical or the accuracy of the algorithm, but this portion of the webinar, I would like to show you how you can use this in Settle3. So when we go to this CPT simulation tab, you will be given the simulated at CPT point, and you also have edit simulation edit settings. And in the settings, you will see that there are parameters that users can define for simulating if they like to simulate the tip resistance, slip friction, or forward pressure. And you can select the different options inside of the number of points that you like to generate. So that means if you do a course, so you will see less accurate, you'll be generating less number of points, but it'll be very fast in computation. So this is a surface level check to see if you like to see your fast check on the CPT range of values, or if you like to see a medium set of your prediction along the depth of the soil for the defined location. You can use medium, which will give you a bit more accurate results, but at the pretty relatively fast computation time. And if you're interested in looking at the project and your sole purpose is to just see more detailed CPT points at a given location, then you would choose Define, which gives you the most accurate results, but it tends to be a bit slower than two of the other options that we have previously selected. And also we have the density with depth and cutoff that allows the users to simulate along the depth, whether they want to choose the user-defined or minimum or maximum. So the minimum and maximum definitely means if you have, let's say, one CPT point that goes up to 10 meters, while the other CPT point goes up to 20 meters. In order to save the computation time, that we allow the users to define whether they would like to see just a simulation point up to 0 to the shortest or the smallest depth of the CPT point, or they would like to go beyond and they would extend that CPT to further down the CPT range. So we allow the users to define that depth as well. And as you can see, if you choose these options, then it pretty much gives you, if you hover over to this eye icon, it gives you the option of seeing what exactly is entailed with each of these options. So of course means you're simulating the points off of 100 simulations with 40% estimated scale of fluctuation, which means you'll have more distribution of the data points with less number of simulations. So that basically means the accuracy might be a little bit lost, but it's very fast in outputting the results. Up to being 500 simulations, and you use a reduction of 18% in the estimated scale of fluctuations. So things to keep in mind when using these options, and also choosing the depth cutoff to select the option that is suitable for the needs, whether it'll be computationally efficiency that you're looking for, or whether you actually like to see the accuracy of the results. And how the users can define that is in the Settle3, in the plan view on the left-hand side, this top-down view, you have these red legends that are given as the given CPTs, and the blue ones are the location of the simulation CPT. So the CPT simulation points are shown in the plan view as the following, with the blue legend here. And when you plot in between the points and you try to graph it, this graph shows you the given CPT that is in red and the simulated CPT, which is in blue. Now, as you can see, this is very close to the given CPTs, except that there are some peak values. Sometimes they are really hard to catch because of discretization, and this peak value, this source, is marginally defined for the very small depth. So sometimes the simulation can not be able to capture such intricate details of each of these points. But as you can see, the general overview of how the simulation can follow the realistic data is something that we were able to achieve with this fine setting that we have run with Settle3. So empirical settlement with CPT points is a new interesting feature that we have in Settle3. So as long as you have the CPT points, what this feature will allow you to do is to generate a soil settlement profile for any region that the user defines. And what it's doing is, in the option, you have the option to choose the empirical method that you want to analyze with the load type, and then you define the width and the length and the pressure. And what this will do is this will apply that set of a load for these number of grid points inside of your defined region. And this is a very useful tool because if you have the CPTs, you don't have to necessarily go through all the struggle of what we previously discussed about this CPT layering system with CPT points. All you'd have to do is, as long as you have the CPTs, you'd like to see what would be my general overview soil profile given the CPTs for the defined region. And you can quickly do a surface level check and see, okay, if I were to run an empirical settlement for that defined load magnitude and the size of the load applied through all of the grid points, then you'll be able to see the contour of the settlement profile for the given CPTs. And the settings that the users can define are very similar to what we previously discussed in CPT simulation. So the coarse, medium, fine, each coming with less accuracy to most accurate results at the time of the computation. And the density depth is also defined in this one as well, but you would notice that there is a unit weight option added on, which means the soil profile along the depth of the soil, if you like to have variable unit weight, you can unselect this. Because, of course, this will come at the cost of computation, but at the same time, this will give you a bit more accurate results when it comes to analyzing empirical settlement for each of these grid points. Again, this is how the user would go about defining the region. And these are the given CPT points. And you'll see this as results. So when you run the compute, then you will see each grid points are applied with the load definition that we have previously set from the dialog. And each are applied with that load. So you can think of it as a moving load pretty much of each individual grid points representing the settlement for the defined region. So these are all going through, and then you'll be able to see the settlement values for each of these grid points. And you will see that they are the maximum empirical settlements with the maximum mean values. And do note that these values, each value represents the average of all of the simulation that has been run. So that means if you were to use fine settings, that means this 500 simulation has all been ran, and they have been averaged to give you the average value of your grid points settlement for that empirical settlement. So let me quickly go through the demos and showing you how the CPT simulation can be analyzed, and also show you how the empirical settlement can be shown in Settle3. So if you take a look at this Settle3 model that I have, we go to the CPT option, and you will actually see that we have 3 CPTs that are defined already, which is shown in this orangish brownish color. And these blue lines, or the blue legends, are the simulated CPTs. And they are generated simply by going to the CPT simulation, and you go to simulate at CPT point, and you will be able to select the parameters that you'd like to simulate. For the purpose of demonstration, we'll just simulate the QC, but these other parameters can be simulated as well, but it depends really on how fluctuating your data point is that will contribute to additional computation time. So let's choose a medium with minimum cutoff, and then we'll choose at any location, maybe around between C3, 5, and C6. And then it will simply do the computes. And right away, you can see that simulation has been ran. And in order to see the results, you simply go to right-click on this, and you go to Graph the CPT. And you'll see the CPT that has been generated. And if you go to multiple charts mode, you can simply click on multiple CPTs that has been generated and see the range of your generated CPT and the real CPT values that you have to show that the simulated CPT and the given CPTs are somewhat in between the points. So this will give you some idea as to how to run the CPT simulation. And if you want to extend this data further, you can simply select on the maximum depth, and that will be able to generate the additional data points for these missing CPT points. And do note that because we are using vertical correlation factor as well, so if there are missing CPT points, sometimes the simulation can be a bit out of range. And that's something to be always aware of, is the statistical analysis, the nature. So in case if you are interested in looking at all of the simulations, you can go to the Expert Excel, and you can go to Expert Simulations, and that will give you all of the data set of the 500 or 300 simulations that you have ran. So if you're interested in not just looking at the average values that we see from this graph, but you'd like to see all of the simulations, you can do so by just going to the Excel and go to Export All Simulations. And what you have noticed also is that we have a low empirical sentiment region that find here as shown. So this is just done by this edit sentiment region, and you add the sentiment region, and then you'll be able to define that along any given CPT point. And then as soon as you define it, then you'll be seeing these grid points. And once you define the region and then you compute the CPT and you view the results, then you will get something like this, where you have these empirical sentiments defined for that region, and loads applied at each of these grid points. And as you can see, if you zoom in, you will see the empirical sentiment applied values shown at each of these points. And note again that these are average values of 500 simulations that we have iterated through to get the results. So if you are interested, you can go back and then use a CPT simulation feature to export what is the distribution of CPT points that I'm expecting to see. So just a couple of examples on a bit more complex models with more CPT points. You can do so by simply defining any region that you want, and you will be able to see the nice distribution of the settlements or empirical settlement of Settle3 with the CPT simulation feature. So that concludes the new feature presentation of Settle3 with the CPT simulation. Now I'd like to pass on the presenter to Dr. Cheng, who will cover a bit more in details on how it's being done behind the scenes of Settle3 and what algorithm that we have implemented to achieve these results.
Yeah, thank you, Steve. And good morning. Okay, I will spend some time to talk about technical background for the random field simulation in Settle3. My name is Cheng. Professor Kiki Fong in Singapore is my co-workers in this research aspect. And I also want to thank my collaborators, Professor Yoshida. And by the way, he is he supports about the GPR, Gaussian process regression. I will mention this GPR later. Also, Professor Armin Still-Lian, he support the case study. Also, my graduate students. Okay, throughout this technical background, I will use this very simple example to demonstrate the new feature in Settle3. This is a Hollywood site in South Carolina in United States. This site, there are 5 clusters of CPTs, And those are the 5 cluster CPT. And each cluster, there are 5 CPTs. We will, in the demonstration, we will pretend that the central CPT is unknown and the remaining 4 are known. So all the dark lines here, you see, are the known CPTs. The red line, they are the CPT locations that we want to simulate. In the demonstration, we pretend that they are unknown. Okay, so this new feature in Settle3, its main function is to simulate given CPT parameters at sample locations. I mean the dark lines. Given the dark line data, we want to simulate a CPT parameter at n sample location, such as we want to simulate those red locations. Okay, and what we do is to do conditional random field simulation, and this just give you a sense what it does. Say for instance, at this cluster 1 central location, this green line is 1 conditional random field sample for the cone-tip resistance. And you can simulate this cone-tip resistance once. You get 1 green line. You can simulate it for hundreds of times to get hundreds of green lines. Based on this hundred of green lines, these are the median value. Dash line is a 95% confidence interval. So this is what this new feature and Settle3 can do. Basically, it simulates conditional random field based on known data. So the basic, the computation engine behind the thing is quite simple. In principle, it is quite simple. It assumes that the CPT data consists of 2 parts. One is the trend, the other is the spatial variability. By trend, I mean this is the trend function. Spatial variability is the oscillation around the trend. And the calculation engine, it has a model for the trend, and also it has a model for the spatial variability, which is W. We use the random field model. For the random field model, it has 3 types of parameters. The first type is called the standard deviation of the spatial variability. The second type is called the scale fluctuation. Some people call this correlation length. The third type of parameter is called smoothness. And what do they mean? The standard deviation of W, it controls the magnitude of W. Say for instance, this is a spatial variability sample for a smaller standard deviation. This is for a larger standard deviation. As you can see, the effect of standard deviation is to control the magnitude. This has larger magnitude, this has smaller magnitude. The second is a scale of fluctuation. It controls the correlation length of W. Say for instance, this W, its correlation length is really small. But for this W, the correlation length is really large. Smoothness controls the roughness of W. For this guy, the roughness, the random field is rough. So now smoothness is small. For this guy, it is very smooth, and the smoothness parameter is infinity. So these are the 3 parameters for the spatial variability part. For the trend part, we also adopt the so-called Gaussian process model, Gaussian process regression model. It is actually also a random field model. It is an independent random field. So this model is kind of interesting. We assume that the total data consists of a trend part and the spatial variability part. Both are random fields, and they are independent random field. The main difference is that for the trend part, we assume the smoothness parameter is infinity. That means it is very smooth. That's the main difference. The trend part has also its own standard deviation, sigma t, and the scale fluctuation, delta t. This is the so-called Gaussian process regression is actually a quite well-known regression method in machine learning. This is one picture that I copy and paste from Google. This is a one-dimensional Gaussian process regression for the data. You see, this is the regression result for those dotted data. And the trend function, it can be one-dimensional if you have just one CPT. If you talk about lots of CPT in three-dimensional underground space, then this trend function is three-dimensional. So this is the basic model. So given the model that we have a trend model and a spatial variability model. Both are random fields, and the calculation engine in Settle3 for conditional random field simulation, it has two steps. The first step, step one, is to do parameter identification based on the measured CPT data. Given the dark lines, this step one will identify the unknown parameters. Say, for instance, it will identify the random field parameters for the spatial variability, including the standard deviation, horizontal scale fluctuation, vertical scale fluctuation, horizontal smoothness, and the vertical smoothness. But all the process done in the step one is behind the scene. You will not see it in the Settle3 software. But you need to know that there is a step one in this engine, which does this parameter identification. And this step one not only can identify the parameters for the spatial variability part. Say, for instance, this is the identification results for this data. This is vertical scale fluctuation, vertical smoothness. It can also identify the parameter for the trend part. And this is the trend parameter for this particular example. And okay, after, again, I want to emphasize all these, you cannot see it. But all this is behind the scene of Settle3. The step two of the engine is to do conditional random field simulation. This is what you see, what you really see in Settle3. By conditional simulation, we mean that the calculation engine is able to simulate unsampled location by conditioning on the sampled data. Say, for instance, there's no CPT here. You don't really know the cone tip resistance. But given the based on the computation engine of Settle3, you can simulate lots of content resistance samples at that ensample location. And this ensample location can be here or there or there or there. Okay, I want to use this page to show you the effect of conditional random field simulation. Say, for instance, suppose we intentionally pick the simulation location to coincide with one of the known CPT, and this is what you will see about the conditional random field simulation results. All the simulated content resistance will be identical to this guy. And this is reasonable because you are simulating a location which is known. So this is completely reasonable. What happens if you change the simulation location a little bit to the right? This is what you will see. This green line is one conditional random field sample. You start to see some randomness for different conditional random field samples. But because the simulation location is so close to this known CPT, the 95% confidence interval is still quite narrow. Now let's consider a simulation location that is at the center of this cluster. This location, we don't really have known CPT data, so you start to see the uncertainty. This green line is one conditional random field sample, and if you simulate this conditional random field for 100 times or 1,000 times, this is the median. This is the median, and this dashed line is the 95% confidence interval, and the width of the 95% confidence interval, it really quantifies the uncertainty. For this particular location, actually we actually know the CPT data. We just pretend that we don't know it. This actual CPT data, I plotted as a red profile here. As you can see, the chance that this red curve is contained within the 95% confidence interval is indeed close to 95%. You see there's some locations that the red line is outside the 95% confidence interval, but the chance is small. Now, in this PPT, I want to demonstrate the effect of you only have very sparse data. Now, previously, we have 20 known CPTs. How about we only have 5 known CPT? What will happen if I still want to simulate this location? What happened is that the width of your 95% confidence interval will become larger. And this is kind of makes sense. This is because now you have less nearby CPT, you have sparse sounding. So it is reasonable that in this case, the uncertainty level grows. And this is the end result of all the conditional simulation at all the central location. I just show you the result. The red line, it showed the actual elevation data. The green line show one sample of conditional random field. You can see the result of the conditional random field simulation kind of makes sense. There's some chance. You roughly have 5% chance to get a red line outside the 95% confidence interval. Okay, very simple conclusion. The new feature in Settle3 is a conditional random field simulation engine. What it does is, given non-CPT data at sample locations, it can simulate CPT parameters at unsampled locations. The engine is based on Gaussian process regression. The step one is to automatically identify the trend parameters and the spatial variability parameters, but this is totally behind the scene. What you really see in the Settle3 software is the outcome of the step two, which is the conditional random field simulation result. As I mentioned to you, as I have shown you, the conditional random field simulation result kind of makes sense because it converges to the measured CPT data if the simulation locations equal. It is the same as the sample locations, and the uncertainties are quantified by the variability in the conditional random field samples. Okay, this is what all I want to say. Okay, thank you.
Thanks so much, Dr. Cheng, for going over the theoretical background and also what's behind the scenes. I will now move on to the Q&A session. So I will try to read off some of the questions that was brought up during the webinar. So the first question that I see is, do you need to have simulated CPTs to run the analysis, or can you just use the actual CPTs? So I'm assuming this question is referring to the empirical settlement calculation. So for the user-defined empirical settlement region, as long as you have the CPTs, the region will automatically generate the settlement values for you. So you don't actually have to go to manually select the simulated CPTs. You can simply do that using the empirical settlement feature. So that only requires you to have the actual CPTs, and the simulated CPT points and the empirical settlements are somewhat of a separate thing, but they are using the same algorithm to pretty much estimate your analysis for you. The next question is, can you put multiple load for this simulation? Unfortunately, this feature right now, it's sort of, you can treat it as individual loads that are moving along each of these grid points. So they are individual loads. So they're not accounting for the influence zoning effect of all of the loads applied at once. This is just the individual loads applied throughout the grid points. So this, I think another attendee had a similar question, so that answers that question. Okay, so the next question is the empirical settlement for isolated load or group effects? Oh yeah, so that's the same thing as what I just explained earlier. So it's not like a multiple load effect, it's just the individual loads for the grid points. But we might look into adding it as an additional feature in the future, but for now, this is just individual isolated footing. And the next question is, can we use elevation data instead of depth for our CPT simulation? So at the moment, all of the data is defined at the datum point of the ground surface downwards. So it is actually depth. What you want to do is probably normalize all your data points to the depth instead of elevation, then you will be able to fully utilize our feature. So next question is, have you verified simulated CPT point versus field CPT? Yes. So that's when Dr. Cheng has gone through the extensive verification models in checking the near field data points with the known and then the confidence interval of the data. Dr. Cheng, please.
Yeah, we actually have tried to verify the visual random field engine for quite some real case histories. We found that indeed the 95% confidence interval produced by the engine that we just presented is kind of credible. It indeed has roughly quite high chance to contain the actual verification CPT data.
Mm-hmm. Yes, thank you for the feedback. And that's one thing also that we would like to extend our feature into adding more options for the users to see. Because right now we were just presenting the average values for simplicity of showing the results. But later on, we would like to include the actual confidence interval of the simulated points so that users are a bit more aware of the range of values that the simulated points are generating. So that's something in the future for this feature. Right. So, Dr. Cheng, this is a question for you. How many different sites have you compared the CRF generated data with the actual data?
Okay, I need to count. I would say at least. So the Hollywood site is one example. We also investigated a very well-known site, which was done by Professor Mark Jackson, which is a Australia site. It has hundreds of CPT. We also verified that site. We also verify a Netherlands bike site with also about 100 CPT. So I would say we have verified quite some sites with many CPTs. What we actually did for the verification is that quite similar to the case that we shown you today. We pretend that some CPTs are unknown, but actually they are known. Then we use the engine to do conditional random field simulation for that CPT, and then we compare to the actual data to do the verification, and we found that the result is usually quite reasonable.
Awesome. Yeah, thank you for your answer. There's another question. So is there any computational difficulty with deep CPTs? For instance, 50 meters deep CPT might have 15,000 individual measurements. So do you see any issues with having a data having more than 15,000 data points for this algorithm?
50-meter deep CPT might have. Okay, that will be an issue. Okay. The algorithm will be okay. If you have say for instance, if you have 100 CPT and for each CPT you have 200 data points, then the computation is okay because the algorithm will only require to deal with a 100 by 100 matrix for the 100 CPT. And also it has to deal with a 200 by 200 matrix for the 200 data points. So in this case, although there are lots of CPTs, the computation time is still not too terrible. But for the case that you mentioned, you have only one CPT, and for that CPT, you have 15,000 measures.
That's a lot, yeah.
Then the engine will need to deal with a 15,000 by 15,000 matrix. Okay, then the computation cost will be huge.
Right. So I guess one thing also I would like to add as well is in case if they have such a large number of data points, they can do some data filtering to not have all of the 15,000 data points.
Yeah. And you can resample the data so that for each something you have less measurements.
Right.
Yeah.
Okay. And this is one question for Settle3, which is, will the program ever take the calculated CPT parameters and put them into soil layers and we can edit them without having to generate the data ourselves? Yeah, this is a question that we received a lot from the customers, but unfortunately at the moment, it's there's a bit of a stretch with the data that we provide for the users along the depth of the soil and what the users would have to define from the definition of the engineering judgment to determine the values for these parameters. So, for instance, Young's modulus. So that's something that, unfortunately, we haven't had a algorithm to predict and collect the information and translate that into soil layers with the appropriate Young's modulus. So at the moment, we currently don't have. Will the program ever have? Eventually, we would like to tackle on this issue as well and provide users with more availability in some of our assumptions that users can use. So the question is, how do we balance the CRF results with engineering judgment and resulting liability if we are wrong? And this just goes back to the nature of statistical analysis in general. It's something that the engineers will always have to face eventually. And as long as, because in Settle3, we do provide all of the data results for you as well for those simulations. So in case, if you're just using the average values, you can proceed and let them know that we are using this source of the conditional random fields, but at the same time, they simulated results, all of them are provided for you. So in case if you want to build more confidence in your results, I would say going into a bit more statistical analysis and being confident about what simulations that we're seeing and presenting those results will be something that you can add on as simulations that is added on with the statistical analysis. So there is always going to be that bit of a risk, but do note that we have done extensive study with this algorithm, and Dr. Cheng has shown through the literature on the verification models and the validation of this method. And what Settle3 has done is basically take that algorithm into the software package that is easy for users to see, and also all of the results can be exported to users. So, that provides a bit of a room for going extent of explaining all of the variability in details, but at the same time, giving you that option of fast producing the results that is based on all of the average of these simulations. Dr. Chi, would you like to add on to that question? No? Okay, perfect. Yeah.
That is a very difficult question to answer.
Yeah. I agree. Yes. It's that's why sometimes, we always joke and say AI can replace, but engineers, we always have to have the engineering judgment to ensure that the simulations are, at the end of the day, statistical, and there needs to be some assumptions and some, underlying, I guess, risk assessment that needs to be in place. Let's see. Another question was regarding Settle3 features. So what is the grid spacing, and can this be adjusted? So the grid spacing, it really depends on number of grids because we allow users to define the number of grids for the different regions. So as long as you know the region size, then you can define the number of grid points, and these are equally spaced out. So that's how you do sort of the back calculation and calculating the grid spacing. Oh, this is a good question as well. So any case study of utilizing the CRF for post-ground improvement CPTs? Dr. Cheng, do you have any comments on this one?
Post-ground.
Oh, it's the question was any case study of utilizing the CRF for post-ground improvement CPTs?
Post-ground. I haven't investigated. Most cases that I have investigated, it is cases with many CPTs.
I see.
Because we need that kind of case in order to do verification. I have many such cases that is about post-ground improvement.
Okay.
Yeah.
Yep. And at the end of the day, even if the CPTs, so as long as you have the CPTs, you can theoretically generate these CRFs and then simulate the CPTs. Yeah, I'm not sure if that answered the question, but that's how you do on the simulating the CPT points. So we have reached the end of our webinar. So we thank you so much for taking the time to attend the webinar and listen to our presentation. If you have any more questions, you can always email us the questions, and all of the questions and answers will be provided for all the attendees who are here today. And the recording of this webinar will be also available on our website. So we encourage you to go onto our website and watch the video again. We thank you so much for the time. And thank you so much, Dr. Cheng, for joining us today and explaining all the details.
Okay, thank you.
Thank you. Okay, thank you, everyone.